This is the video for the discrete case of whole life insurance. We'll also talk about term insurance and discrete case for deferred insurance. So for whole life, we're going to assume the period is annual, although we can assume smaller periods as well. We're going to define the random variable for the present value of $1 of whole life insurance paid at the end of the year of death for a policy issued to the insured whose exact age is X. So if we draw an age diagram, then at this time the insured is age X, and their birthday that they're going to live to is their Kth birthday, and then they're going to die between that birthday and their next birthday. So death is going to be somewhere in here. So that would be the age last birthday, and K is the future birthday. The $1 death benefit is paid at the end of the year of death, so we're going to have to discount it back K plus 1 years to the current age. And so that's why my random variable z sub x, without a bar on top, is v to the kx plus 1. We have to discount it back kx plus 1. Now remember the probability of this being the last future birthday. We denoted that by the Curtate probability, and this is a notation for that for the probability of this being the last birthday. So if I want to take the expected value of present value random variable, then I need to use those probabilities. So I'm going to just take the probability. Let's see, I'm going to have to erase something here. Okay, I'm going to have to take the probability, multiply it by the random variable, and then add them all up. K begins at 0 and goes to omega minus 1 or infinity if we don't know omega minus 1. Now remember what this probability can be written as. Oops, excuse me. Sorry about that. This probability can be written as I survive K years, then I'm X plus K years old, and I die within a year. So that's what this sum looks like in terms of P's and Q's. Okay, so we take the expected value of the random variable squared, then this is the second moment, and we can use the laws of exponents, and we can write it as follows. See, V squared, if I use annual effective interest, V is 1 over 1 plus I, so if I square it and then raise to the K plus 1 power, this is what that would look like using an annual effective interest rate I. And notice if I go ahead and square that out, I get 1 over 1 plus I plus 2I plus I squared. And then all of that is raised to the K plus first power. Can't get it on there, I've written too close to the edge. But my point is that when I'm taking the second moment, I is replaced with 2I plus I squared. Now if we were using a continuous force of interest, if you recall, when we take the second moment, we replace delta with 2 delta. So that's the difference between working with a continuous force of interest and an annual effective rate when we're dealing with the second moment. Again, the variance of z is the usual. It's just the second moment minus the expected value of the variable squared. And we can write these in terms of P's and Q's, and we should, rather than the summation notation. So if I just write that summation notation out, it's VQX plus V squared px qx plus 1 plus v cubed px2, qx plus 2, etc. So we should be able to recognize that. And then I can start factoring with the second term. I can factor a v and a px out of this second term, and that leaves me with a v and qx plus 1. And then the third term, I can factor also a v and a px out. And in the third term, that's going to leave me with a v squared. Now, how do I factor a px out of px2? Well, remember, the p's are multiplicative, so that's going to leave me a px plus 1. And then I have qx plus 2. Now I could factor it out of another term if there were a fourth term here. I'll show you what that would look like. I would factor a v px out, and that would leave me with a v cubed. And when I factor the px out of px3, it will leave me px plus 1, 2. And qx plus 3. Now, if you don't see that right away, I'll let you go back and see and let you think about that term, the fourth term, and see if you can understand where I came up with that factorization. And you can do this with the rest of the terms. So I'm just going to put dot, dot, dot there. Now I'm just going to take the v qx, and I'm going to take this factored part and remove it. And that's going to leave me with what? A v qx plus 1 and v squared px plus 1 qx plus 2 and a v cubed px plus 1, 2 qx plus 3, etc. And then what is in the square brackets here? The square brackets look an awfully look like what we have up here for ax, except x has been replaced with x plus 1. So this is the actuarial present value of whole life issued to age x plus 1 in brackets. And therefore I can write down my final recursion formula. I just replace what's in brackets with a x plus 1. So by factoring out the VPX in the terms 2 and onward, I have produced this recursion formula. Notice what the recursion formula says. It says, I get this if I die in the first year, or if I live through the first year, I get a whole life policy issued at age x plus 1. So it makes a lot of sense when we view it that way, and it's easy to remember. Okay, so let's look at term insurance where the benefit is paid at the end of the year of death, and we're using the Curtate probabilities to find that year of death. So we define the random variable for the present value of $1 paid at the EOYOD of insured age X if death occurs within n years. Notice that if death occurs here n years or later, in other words, I celebrate my nth birthday from nth future birthday, or any other future birthday beyond that, the contract has ended. So my benefit is actually 0. So the contract ends once I celebrate my nth future birthday if I have n-year term insurance. Okay, so what do? Well, we just truncate the sum above. We have our expected, notice the random variable looks a lot like the term insurance random variable we've seen before, except there's no bar on top to indicate the continuity part, the continuous part, because this is the discrete case. So the discrete random variables and the discrete symbols don't have that bar on top. So the actuarial present value of this random variable, again, I can just copy down the formula for whole life and just truncate it. And so the last birthday, future birthday I can celebrate and still get a benefit, or my beneficiary is my n-1st birthday up here. So that will be, the benefit will be paid at nth future year. I will have survived to my n-1st birthday. and then dot. So that is my last Q. So that would be in terms of my P's and Q's. Likewise, we can have a variance formula. We just take the second moment, we just square the V's, or square those terms above to get the second moment and subtract the square of the expected value. So that's no big deal. Oh, here we can, we probably should get used to seeing this in sigma notation. So in sigma notation, K is going to go from 0 to my n minus first birthday, because that's the last future birthday I can celebrate. The benefit is paid at the end of the year, so at time K plus 1. Okay, so that is what it looks like in sigma notation. So we'll see this a lot. We should get used to seeing that. Okay, let's go to the second page. Page 32. It's helpful to recognize these term insurance in terms of just P's and Q's. So in other words, it's helpful to just recognize 1-year term, 2-year term, 3-year term. That way you don't have to think too much about what you're doing. So for 1-year term, if you die in the first year, you get the benefit. The probability of dying within the first year is QX. And then the present value of the benefit, well, it's paid at the end of that first year. So that's the probability of dying in the first year times the present value of the benefit being paid at the end of the year. So VQX, or QXV, is 1-year term insurance. 2-year term insurance, well, you can die the first year and get the benefit, or you can live through the first year and die the second year. And if that happens, then the present value of the benefit is V squared, because the benefit is being paid at the end of year 2. So those are the two mutually exclusive events that can happen, so that you can, your beneficiary can get the benefit. So what I want you to do is now pause it, and I want you to write down 3-year term insurance in terms of your P's and Q's and V's, just like I've done for 1 and 2-year term. Okay, so if you paused it, then this should be what you got for 3-year term insurance. All you do is you add 1 term to the 2-year term insurance term. V cubed px2 qx plus 2. So hopefully you're able to do that. Now let's notice the recursion formula for term insurance. Let's factor a VPX out of terms 2 and 3 here. Okay, so a factor of VPX. Let's see. Out of this second term, it leaves me a V in QX plus 1. And factor of VPX out of the next term, it leaves me what? V squared PX plus 1 QX plus 2. All right, so let's just do what we did before. Let's factor the VPX out of both terms. And in brackets, I'm going to have V QX plus 1 plus V squared PX plus 1 QX plus 2. And what's in brackets looks a whole lot like 2-year term insurance, where X has been replaced by X plus 1. And indeed, it is. So the recursion formula for 3-year term insurance looks like this. So it's 1-year term, plus if you survive the first year, you get a 2-year term policy. Whoops, I messed that up, didn't I? Your age X plus 1, and you get a 2-year term policy. So that's what it should be, the subscript. So in general, the recursion formula for n-year term is going to be V QX plus, if you survive the first year, VPX Now your age x plus 1, and your original term was n years, so you have n minus 1 years left on the contract. So that's what the recursion formula is going to be for n-year terms. See if you may need to pause and think about that. Make sure you understand this recursion formula before you go forward. Okay, now think about this. What if you have n-year term insurance and you want to, let's say, break it up into m-year term insurance and what's left over. So m-year term insurance. Now, how old are you? Your age x plus m, right? So I'm going to leave a blank space here in front, but I'm now age x plus m if I survive that m years. And how much is left in my term? There's n minus m left on my term. Okay, so why did I leave this underline here, this blank space? Because this is issued at age x plus m. And so I need to discount it back with interest and survivorship m years. And so this is what my recursion formula would look like if I wanted to use m-year term insurance rather than 1-year term insurance, as I have above. And of course you can derive this using p's and q's and v's and factoring out the appropriate thing. You would actually factor out this expression from each of the remaining terms. But just again, think about that. Make sure you understand it. We can talk about it more if you wish. Okay, so let's go to n-year deferred whole life insurance. So this provides a benefit following the death of X only if it occurs at least n years after issue. So the deferral period is n years, and if death occurs there, there is no benefit paid. So here, my values for the number of future birthdays, 0, 1, all the way up to n minus 1, and there is no benefit paid. But if I survive to my nth birthday, now the contract goes into force, and the benefit will be paid to my beneficiary at the end of the year of death. So I have my v to the k plus 1 being the present value of that $1. This is the symbol for the random variable. Notice there is no bar above it because this is, again, is end of the year of death insurance and not instant of death insurance. And I denote the expected value in the usual way. And also notice that I can view this as being a pure endowment of what? A whole life policy issued at age x plus n in the future. So this is a very similar formula that I had for the instant of death insurance. It's just that there are no bars above the A's. I can rewrite whole life in terms of these two, just as I could for instant of death. So here is my deferred. Here is my term, n-year term, and n-year deferred. And notice this adds to 0, so that I get v to the k plus 1. And this v to the k plus 1 also adds to this 0, so that I just get, no matter when I die, v to the k plus 1 for my random variable. So therefore, my random variable for whole life is equal to my random variable for n-year term plus my random variable for n-year deferred whole life. And if I take the expected value of both sides of this equation, I get ax on the left side. I get a x in 1, or the term life and deferred whole life. So same relationships that I had for instant of death insurance. Probably don't need to look at that too much, but just make sure you can see when you add those random variables together, you just get v to the k plus 1 no matter when death occurs. Okay, finally an example. Here we're going to take a constant force of interest. Remember the analogous The analogy to the constant force of interest as far as probability distributions is the geometric distribution. But if I recall, my constant force is mu. Then I have the exponential distribution. So that's my PDF. Let's see. There's my PDF. And then my cumulative distribution function for the exponential, and my survival distribution function, and my actual present value for $1 whole life is mu over mu plus delta. And then for pure endowment, probability of living n years, v to the n. And so that's just going to be what? E to the minus mu n, e to the minus delta n. And you can add the two exponents together using the laws of exponents. So for the discrete case, I'm just going to have a constant probability of death each year, Q. So that's, rather than a constant force of mortality, I have a constant probability of death at each age. So these are analogous to one another here. And then my probability of surviving to the next year is just 1 minus Q. It's also a constant. So I can write out my whole life formula in terms of my P's and Q's. VQ plus V squared, and then I would normally have PX Q, but PX is 1 minus Q times Q. And then for my next year, I would normally have PX2, but PX2 just means I survived 2 years. So that'd be 1 minus Q squared. And then I died in the 3rd year. And I would just continue this. And then you can factor a VQ out of each term here. And we have a geometric sum with common ratio V times 1 minus Q. So I have VQ times 1 over 1 minus the common ratio. Now what I'd like for you to do, see if you can simplify this, and it will simplify the whole expression here will simplify to Q over I plus Q. So see if you can simplify that algebraically. It's a good exercise for you. And the final thing to note is if you calculate the second moment, remember all you have to do once you've calculated the first moment, you could go through the whole calculation again. But remember, if you have annual interest, you just replace I with 2I plus I squared to get the second moment. Okay, so this is the end of the lecture on an introduction to end of the year, death, whole life. And might want to go back and look at parts of it that seemed difficult to you or that you didn't understand, and have your questions ready, and we can look at it. Start on your exercises for section 7.1. Hopefully you can make progress on those to reinforce some of the things we've talked about.